Hello, my name is Yavo Kammer, and in this talk I will try to explain how prediction statistics can help us cope when we are shaken, scared and irrational. To give you an overview of the talk, we will first consider what the public wants and what we as scientists can provide. I will then demonstrate how predictive skill is calculated. We will look at experimental data to see how skillful the general public is. And lastly, I will talk about how we plan to communicate these findings to the public. What do people want during an earthquake crisis? First and foremost, they want to be safe. They want to know when the next earthquake is going to happen. If they are poor and can't afford it, telling them that they need to live in better engineered buildings may not be of much help. In addition, they want some kind of rationalization to give them peace of mind. They may find it confusing that thoughts are being slowly loaded by the movement of tectonic plates, but at the same time they are somehow always ready to go, even after a large earthquake has just occurred. They may find simple yet absolute reasons, such as the wrath of God, more appealing. What can we provide as scientists? Much like weather forecasts, which tell you the probability that it will rain tomorrow, statistical earthquake models can provide probabilities of earthquake occurrence within a given space-time window. If you are considering whether to sleep in your car or go back inside after a large earthquake, such forecasts can help you make an informed decision. The RichterX platform employs the epidemic type aftershock sequence model to provide the public with earthquake forecasts for anywhere in the world. The model is updated on an hourly basis using the USGS catalog. For more information about the platform, click the link in the video description. In addition to public dissemination of operational earthquake forecasts, the platform serves as a benchmark for assessing earthquake predictions. We organize a global earthquake prediction challenge that invites anybody with an idea, data source, or a model to submit earthquake predictions. With this challenge, we aim to achieve three main goals. First, accelerate the development and testing of earthquake prediction methods. Second, improve our global forecasting model using successful earthquake predictions as a feedback. And lastly, counter unfounded claims of skillful earthquake prediction by providing a skill record. How do we measure predictive skill? Here is a simple example with three predictions. The first one is in Afghanistan with a 50% probability. The second one is in Greece with a 16% probability. And the last one is offshore California where the probability is 5%. Let's express these probabilities with physical objects. A coin, a regular dice, and a 20-sided dice. We put a mark on one of the faces. Now the ratio of marked faces to all faces is equal to the probability. For simplicity, let's switch the coin with the dice and mark 3 of its 6 faces. Now we have 3 predictions and their modeled probabilities. Suppose somebody predicted 2 out of those 3 correctly. Are they skillful or not? Let's see. What did we expect according to our models? If we make 10 predictions, each with a probability of 0,1, we expect on average 1 to come true. So, here we have 3 predictions with an average probability of 0.24, which means that we expect on average 0.72 hits. The predictor got 2, so they have 2.8 times more hits than we expected. This is what we call information ratio, or in other words, observed over expected ratio. So it looks like our predictor has skill, right? Well, not so fast. We need to consider another important question. How surprising are these results? Or in other words, what is their significance? How do we measure the significance of a dice? With a caliper? With a voltmeter? How about an old yogurt cup? Well, if it's an actual dice rolling machine, then yes. The technique is simple. We roll the dice and look at how many hits we get each time. We repeat this several times and record how often the observed hit count was less than 2, which is what our predictor got. If you have enough time, you can do this by rolling the dice, or with a Python code. We didn't have much time, so we had to use MATLAB. And this is how we calculate significance, or 1 minus p-value in statistical terms. It turns out getting 2 hits out of 3 dice is not such a big deal. We would need a bare minimum of 95% significance for it to be a noteworthy performance. You can imagine that our results and conclusions would change depending on the type of dice we were rolling. That's why it is very important to assign correct probabilities when evaluating predictions. Now that we know how to calculate predictive skill, let's look at actual earthquake predictions. For the last 2 years, we have been organizing a fully prospective global earthquake prediction challenge at richterx.com. We have accumulated over 10,000 predictions from hundreds of users around the world. In the top plot, we will show how the information ratio evolves with time as more and more predictions are submitted and evaluated. A value of 1 would correspond to the model expectation. At the bottom, we will plot the significance. Anything below 95% will be insignificant. These graphs tell us that, considered together, our participants perform as good as our forecasting model would expect them to. We can also look at the predictive skill of each participant individually. For instance, currently, this participant has significantly more true predictions than our model would expect. And, although the information ratio is not very high, we can study these predictions and gain insights to improve our forecasting model. In addition, since we are tracking all the hits and misses, the public knows that this participant has an average hit rate of 51%. Predicted or not predicted? Since we are keeping a live database of predictions, whenever an earthquake occurs, we can check if the earthquake was predicted or not. And if it was predicted, we can inform the public about the predictor's track record. For this purpose, we have set up a Twitter account with the handle @predictedornot. You can send us a follow request if you want to be amongst the first users and provide us with your valuable feedback. In this way, we can provide the public with the necessary information to counter unfounded claims of skillful earthquake prediction. Furthermore, we can encourage interested people to take part in the challenge of earthquake prediction, appreciate its difficulty, and hopefully contribute to its solution. Thank you very much for your attention.